Hello, and welcome back to 6.4. In 6.3, we learned how to apply the central limit theorem to quantitative data for sample means. And now we're going to look at the central limit theorem for sample proportions. So Alex will follow what we're doing in this lesson. This is the one lesson that the ebook does not follow the same. It talks about the binomial distribution, but we're working with just proportion. So you'll just follow this. So some notations that we need to know are p hat represents the sample proportion. And x is the number of successes, and n is the sample size. And x over n is p hat, like I said, is normally distributed. With p, our population proportion will replace our sample proportion. And then this is our standard error. So it's our standard error of the sample proportion. So there's three conditions, just like there were in the last section. The first condition is that we have to have a random sample. The second is that they have to be independent of one another. And the third is that the sample size has to be large enough. And we have to prove that with n times p times 1 minus p has to be greater than or equal to 10. Okay. We are going to describe our sampling distribution similar to what we did in lesson 6.4, where the sampling proportion, the average of the proportions will be the p hat, and the sigma, or the standard deviation of the proportions, is going to be the square root of p times q divided by n. And remember that p hat and then q hat is equal to 1 minus p hat because they're complements. Let's jump right into example here. In 2014, a Pew Research survey asked 1,821 random 18 to 33-year-old Americans if they believed in alcohol was more harmful to a person's health over marijuana, and 69% said yes. Verify that the conditions of the central limit theorem for proportions are met. So the first one is, do we have a random sample? And they did say that they took a random sample. Second is independence. If you ask someone the question for the survey, you cannot ask them again. So it's without replacement. So we have to show that 20 times our sample size so 20 times 1821 is 36,420 is definitely less than all of the Americans out there. So we've checked that off. And then the third thing is normality. So we have to prove that we have a normal distribution. And so that is n times p times q has to be greater than or equal to 10. So n was 1,821 times p, which is 0.69, times q, which is 0.31. And that comes out to be 389.51, which is definitely bigger than 10. So we can use the central limit theorem. So we're going to describe our sampling distribution. So p, the mean of the p hat is going to be equal to p hat, which we said was 0.69. And the standard deviation of the p hat is going to be equal to the square root of p hat q hat over n. And so in our case, that would be 0.69 times 0.31 divided by 1821. So we would say that P hat is normally distributed with 0.69 as our center, and then this will be the standard error. And so he says, suppose you conduct your own poll of 1,821 random adult Americans, 18 to 33 years old, now, and find that 67% of them believe that alcohol is more harmful to your health than marijuana, which would be unusual with a probability of 0.032. List 3 conclusions you might draw with explanations. So we said it could just be a fluke, right? The second thing is maybe the true proportion P is not actually 69%. Maybe that's really not true. Maybe it's really lower, like 67%. And the third thing is maybe not a random sample. That's totally a possibility. And this standard error, just if we wanted to write that down, that would be 0.0108. But this is what we would use in Desmos. Look at a good example here. It says, according to 2018 Vox poll, 45% of Americans report watching the Super Bowl yearly. Suppose a sample of 120 Americans is randomly selected. Verify that the conditions are met. So, did we take a random sample? Yep, we did. And second is independence. So 20 times our sample is 2,400. We definitely have 2,400 Americans. So our sample, 20 times our sample is less than our population. We don't know what the population of Americans is, but we know it's at least 20 times our sample. So we can check that off. And lastly is for normality, we have to show that N times P times Q is greater than 10. And so N is 120, P is 0.45. That means Q is 0.55. And so we can take, that is 29.7, which is definitely bigger than 10. So we're good to go. So let's describe our sampling distribution. So P hat is normally distributed at 0.45. And then our standard error is 0.45 times 0.55 divided by 120. And it says, find the probability that the sampling proportion that watched the Super Bowl is between 41% and 46%. So if the mean is here at 45, we're saying 41 to 46. So the probability that the sample proportion is between 0.41, so these are decimal 0.1 to 0.46. Okay. And I'm sharing the screen with you so we can put this together into Desmos. And we want to know between 0.41 and 0.45, so between 0.41 and 0.46. It looks like we could expect about almost 40% of people, for almost 40% of the samples to have between 41% of them saying to 46% of them saying that they're going to watch the Super Bowl. So let's interpret this together because we've got percents and percents and it gets a little confusing. So approximately 39.79% of the samples will have 41% to 45% of the people who watch the Super Bowl. And what they said, there is a 10% chance that the sample proportion of Americans who watch the Super Bowl yearly in a sample of the size of 120 will be at or below. So 10% at or below tells us that it's the 10% over here. So what proportion of Americans were less than 10% of them, the sample? So the probability that the p hat is less than something is 10%. So that's going to use our inverse norm, or inverse CDF. That would be a p hat of 0.3918 rounded. So about 39%, about 10% of the samples will say that 40% of them are watching the Super Bowl. And then letter E says, now conduct a poll of 120 Americans and find that fewer than 32 of them watch the Super Bowl yearly. Is this unusual? So 32 means that we would have a p hat of 32 out of 120. So that p hat is 0.2666666 rounded, obviously. So if our center is at 0.45, so fewer than this. So what is the likelihood that we would have something less than 0.267, we'll say. So the probability that your sample hat will be less than 0.267. That comes out to be very small. 0.0000. 279. And so that is very unusual because it is less than 5%. And then F says, suppose the scenario above in part E really does happen, list 3 conclusions. So it could just be a fluke. It could be the true P is not equal to 45% watching the Super Bowl. Maybe there's fewer people. And the third thing could be not a random sample. And that concludes chapter 6. Catch me back for some more videos.